If you live in North America, you have likely been told to flip a small switch on your ceiling fan to make it run in reverse during the winter. It is a piece of conventional wisdom that is widely accepted, yet building science data from Harvard University indicates it is physically flawed. This instruction to reverse fan rotation is printed in nearly every energy efficiency guideline, utility advice column, and manufacturer manual across the continent. The stated objective of this practice is straightforward: to push the buoyant, warm air that pools at the ceiling back down into the living space without blowing a cold draft directly onto the occupants below. In thermodynamic terms, the goal is thermal destratification, mixing the separated layers of air to equalize the room's temperature. But when subjected to empirical fluid dynamics testing, this globally prescribed best practice actually fails to achieve its intended result. Researchers at the Harvard Graduate School of Design monitored the precise air velocities and temperature differentials of conventional ceiling fans operating in reverse, finding the practice to be highly inefficient. The winter reverse rule is not an optimal engineering solution. It is a legacy mechanical workaround born from 1980 safety regulations. To achieve actual thermal destratification, the data shows we need to run contoured airfoil blades in the forward direction. To understand why reverse mode fails, we have to look at the first principles of how fans operate. A ceiling fan does not alter the ambient dry bulb temperature of an enclosed space. Instead, fans alter human thermal perception by interacting directly with the skin. This animation illustrates the process. The human body maintains a thin, insulating boundary layer of heat around the skin. A high-velocity downdraft from a fan strips this boundary layer away, accelerating the evaporation of perspiration. This localized physical phenomenon creates a wind chill effect, making the ambient environment feel up to 4 degrees Fahrenheit cooler than the actual temperature of the room. Because the occupants feel cooler, they can raise their air conditioning thermostats by those corresponding 4 degrees, which yields up to 30% in energy savings. During the winter heating season, the physics remain the same, but the environmental challenge shifts to vertical thermal stratification. The hydrostatic equation and the ideal gas law dictate that warm air is less dense and highly buoyant. As a residential heating system runs, the warm air naturally rises and pools at the ceiling, while cooler, denser air settles near the floor. In a room with a standard 10-foot ceiling, this buoyancy-driven separation frequently results in a floor-to-ceiling temperature gradient of 9.5 degrees Fahrenheit. This vertical density gradient forces heating systems into overdrive to keep the lower occupant zone warm. Mechanical mixing is required to equalize the space. If reversing the fan's motor is an inefficient way to mix that air, we have to ask why the reversible switch became a standard feature on American fans in the first place. The origin of the modern fan traces back to the late 1880s, when engineer Philip Deal invented the self-contained direct-drive electric ceiling fan. Deal was employed by the Singer Manufacturing Company, and his initial fan design simply adapted the small electric motors originally built to power sewing machines. These early fans proliferated, but by the 1950s, the rapid adoption of residential air conditioning caused ceiling fan sales to plummet in the United States. It wasn't until the 1970s energy crisis that the residential market revived. Homeowners faced skyrocketing electricity and heating oil costs and sought ceiling fans to maximize the efficiency of their central heating. But in the mid-1980s, regulators intervened. New safety guidelines mandated that any ceiling fan equipped with high-speed, thin metal blades had to be installed at least 10 feet above the floor. Because standard American construction utilizes 8-foot ceilings, manufacturers had to redesign their products to comply. They replaced the fast metal blades with thick wooden or composite paddles, increased the blade count, and steepened the blade pitch up to 16 degrees to ensure air movement at much lower, safer speeds. The aerodynamic result is that if you run these steep, heavy paddle blades forward during the winter, they generate a significant downward breeze that creates an intolerable wind chill draft in cold temperatures. The reverse mode was not engineered as a thermodynamic ideal. It was a legal artifact, a way to draw air upward so manufacturers could continue selling fans for winter use without blowing cold air directly onto the people sitting beneath them. To test the actual performance of this workaround, the Harvard Graduate School of Design evaluated standard paddle fans operating in reverse mode inside a highly monitored, insulated test room. The baseline power consumption for a conventional paddle fan running in reverse on its lowest speed was 11.5 watts. The thermal performance was poor. The fan only reduced the temperature gradient to 7.3 degrees. The floor temperature rose by just 1 degree. The flaw lies in the updraft. Reverse rotation forces air upward, crashing across the ceiling and sliding rapidly down the walls. In the Harvard test, 42 airfoils are shaped like airplane wings, generating lift in one direction. Reversing destroys their aerodynamics. Running the airfoil fan forward at ultra-low speed, power consumption dropped to just 1.8 watts. The vertical temperature differential compressed to a nearly imperceptible 0.2 degrees Fahrenheit. This forward mode ultra-low speed configuration achieved near-perfect thermal distratification. The warm air was successfully pushed to the floor. Because the downward air column was concentrated directly under the fan at an incredibly slow speed, the average air velocity in the perimeter of the room dropped to just 7 feet per minute, eliminating the draft risk entirely. Operating contoured airfoil blades in the forward direction at ultra-low speeds completely solves the thermal paradox. It achieves perfect mixing without triggering the wind chill effect. True building efficiency requires mapping your aerodynamic strategy directly to the architectural volume of the space you are trying to condition. For standard ceilings of 8 to 9 feet, the data shows the optimal winter setup is a brushless DC airfoil fan running forward at the lowest possible speed. But the physics shift again when dealing with vaulted or high ceilings that exceed 10 feet. In a vaulted room, the physical distance between the blades and the floor naturally dissipates the air velocity. To combat the severe thermal stratification in a high ceiling space, the fan must be operated in the forward direction at medium or high speeds year-round. This dependence on architectural and climatic variables is why North American standards differ so sharply from tropical regions, like India, where space heating is irrelevant. In tropical climates, the reverse function is ignored completely. Indian residential fans are optimized purely for high volumetric flow rates, utilizing shallow-pitch, high RPM metal blades designed strictly to maximize evaporative cooling. Ultimately, optimizing a home's climate goes beyond the raw tonnage of the HVAC unit. It demands matching the geometry of the air movement to the dimensions of the room itself.